Okay, great. So our next speaker this morning is Rustan Leino from Microsoft Research. Rustan got his PhD in '95 from Caltech, and then he went to the DEC Search Center, and which later became Compaq Search, and from there he moved to Microsoft. So Rustan is known because he has pioneered a kind of program verification tool that sits on top of SMT solvers and has an integration into the programming environment such that programmers basically interact with a verifier like a text processor has a spell checker. And he has built a number of systems building up towards his vision, starting from ESC Modular 3, ESC Java, later Ruby, Spec Sharp, and now he's working on Daphne. And today he will talk about the next step going beyond programs. Okay.
Thank you very much.
Okay, so to say where we might be going, I thought that we would start with reviewing some things. So we saw this diagram yesterday. So program verification many years ago, and you can see that it's not that structured, but it's the ideas were kind of there. And of course, I mean, you wouldn't try to think of entering these little boxes into a computer like that. Okay, many years later, Tony Hoare's FIND program from 1971. Here's kind of interesting that you see the program, and there are some comments in the program, and they're actually really called comment, and the comments are the loop invariants. So you write down the loop invariants as comments. They're not considered as part of a program text per se. And then you also have something that tells you about termination. What is it that makes the loops terminate? So this says that it increases I and decreases J, and so forth. But there is the program. This is starting to look more like the kind of program that we would type into an editor. A couple of, or 2-3 decades later, this was a slide that I used. I just dug it up last night in 1999, where I was talking about extended static checking, and there is a thing that we used to talk about at that point called the decidability ceiling, which is this, well, imaginary line somewhere between when you try to do more and more things. At some point, you get to a point where the routines that you're using are no longer decidable. Well, that shouldn't stop us from making progress, so we can be above that line. But if you compare the extremes of this diagram, what I call traditional checkers here, at that point, I guess checkers was referring to like type checkers, maybe lint-like checkers, whereas program verification, well, there were tools that you could do this mechanically already then, but they were not commonly used. And so if you were doing program verification, you were probably doing it on paper, maybe using some bigger systems. So extended static checking tried to use that kind of technology, but not go for full checking of the programs. So, but I was looking at, for this slide yesterday, I also found the very first ESC Java demo, so I thought I'd just bring it along. This is one of the slides of it. The first ESC Java demo was given on a slide like this, and the tool actually wasn't quite ready at this point, but the tool did work like this afterwards. So anyhow, that's we can do better today. All right, a few years later, I was working, and well, I and several others in the field were working on using the same kind of technology, but trying to get automation and pushing it towards full functional correctness. What extended static checking had done was to limit the checking so that there would be a bunch of things that you would not check, and so the checkers would be unsound. So the question became, well, could you actually do this for full functional correctness? So full functional correctness is not just sound, but it also means that the post conditions that you write, that is what you try to verify of the programs, becomes much more interesting. It's not just that the programs have no array index bounds errors. So that pushed checking up into this corner where you can use more automation but still get functional correctness verification. Okay, so where are we then sort of today? Well, today there are a bunch of proof assistants that are used regularly that 10 years ago they did not have that popularity in the field, in the programming languages fields at least, formal methods fields. And those proof assistants, and I'm thinking of systems like, say, Coq or Isabelle, They are often applied to programs these days. So even though they're proof assistants and you would do mathematics with them, you can also encode programming languages and do program verification using them. But it's hard work. So from the other end, the automatic program verifiers like Daphne, they have grown into not just doing functional correctness of programs, but also doing meta-mathematics. And I'll show you some of that. And in fact, you can use a tool, a program verifier like Daphne, if you want to prove theorems about mathematics, well, about certain kinds of mathematics, and get a lot more automation in this way. Okay, so what are some systems that are written in these ways? There are several large, tricky systems that have been verified with mechanically with verifiers these days. Here I'm just listing a small set of them, although these are quite important ones. So CompCert is a verified C compiler done in Coq. SEL4 verified is a small microkernel, single-threaded microkernel that was verified in Isabelle. And Ironclad and Iron Fleet were two projects done at Microsoft Research for verifying end-to-end security of applications, both sequential and distributed code. Now, the difference between these that I've highlighted here is that the first two were done by formal methods experts, whereas the Ironclad and Iron Fleet were done by 8 systems programmers. Actually, one of them had expertise in formal methods, but the others were just regular systems programmers who come in and use specifications, use proofs, and so forth in the tool. So the fact that they can use tools like this, I think, shows that we have come a long way from where we have been. Okay, so enough talking about that. So I'm going to just show you some things so we can use that for the rest of the discussion. So I'm going to show you some demo from using Daphne. And let's see, is this readable from the back? Oh, it's good. All right, so what I will do is just show you a few things that you can do with program verification, and then we should go on to see how you can verify things beyond programs. So this is going to be the well-known Dutch flag algorithm, which is also known as the pivot algorithm in Quicksort. So the idea is that you have an array of colors. So the colors are red, white, and blue, as in the Dutch flag. And you can think of them as the white being the pivot of the quicksort algorithm, and the red being the numbers that are smaller than the pivot, and blue being the things that are greater than the pivot. And we want to sort these. So what I've done is I've defined a predicate order that's on these 3 colors, and here we have the method of array colors. So the first thing that we do when we write the specification of, when we write down the method is we're going to write the specification. So I will write a post condition, which I give with the ensures keyword, and I will say that for all indices into the array, it will be the case that A, I, and AJ are ordered. So that's something that I just write down. So now I've written down my intention, and you can see already that from what I was saying, say 10, 15, 20 years ago, this is a functional specification of what's going to happen. This is not just checking that some array bounds are going to be in or out of bounds. Okay, but I get errors, complaints right away, and I'll read you the small text. It says it's complaining that the object may be null. Well, these are the sorts of boring things that happen, but if you write down the specification, you want the specification to have a meaning. So you don't want it to be undefined if someone passes in null to this method. Well, of course, we really intend for no one to call this method with null. So we just give a precondition. And this is good software engineering practice. You write down preconditions. If you do nothing else, write down preconditions and think about invariants when you implement things, and you'd be a better programmer. Of course, good programmers do this. So here's the precondition, and I write it down, and now all of a sudden the postcondition makes sense. I will add one more thing here, which is I will say that the method is allowed to modify the elements of the array, because of course we're going to sort it. How else are we going to do it? Let me just up a little bit so you can see it a little bit better. Okay, so let's write a little bit of the code. well, I started writing the body here, and immediately it complains that the post condition doesn't hold. Well, of course, give me a chance. I haven't started yet. So, okay, so what we're going to do is I'm going to show you just the beginning of what you do here. And the important thing is that you write down the invariant. In this case, it's going to be a loop invariant. So what I'm going to do is I'm going to introduce 3 variables, red, white, and blue. And I will set these initially to 0, 0, and the length of the array. And here's the idea. I want to keep track of the sorted elements that I've sorted so far that are red. I'm going to put left of the index R. And between R and W, I'm going to put all of the white elements that I've sorted so far. And then between B and the length of and the end of the array, I'm going to put all the blue ones. So the part that's unsorted is the stuff that's between W and B. This is the key. If you remember that of the algorithm, you can just write the algorithm yourself. So here it is. So we continue doing stuff until, I mean, for as long as W and B are not equal, because when they're equal, then there's no unsorted portion left. But what we need to do now is we need to write the loop invariant. And the loop invariant really helps guide the writing down an algorithm like this one. That is, you have to have a clear picture of what the loop invariant is. Otherwise, you will not be able to write the code. So here I will just say that all of these indices are ordered, and they lie in that succession. Okay, that's one of the things we're going to need. This is a kind of boring loop invariant to write down, but it's so straightforward that you just do it. Okay, here come the more interesting ones. I'd like to say that everything left of the index R is red. That is, those are the red portions that we've done already. So between 0 and R, we want that AI is indeed red. Okay? And I want something similar for the other two, so let me just copy this a couple of times. So between R and W, that's where all of the white ones are going to be. And the blue ones are going to be between B and the end of the array. Okay? So this is the key. Once you've written this down, you can now just think of the cases and just make sure yourself, even if you don't have a verifier, that you're doing the right thing. But in the interest of saving a little bit of time, I'm going to pull it out of the oven, like Martha Stewart here. There it is. Okay, so that's the code. But again, this last part, I would demo that too, but I've got other things to say. So you would write just according to the invariance. And you can see that if you want to interact here with the verifier, I mean, suppose that I didn't include one of these lines, well, then the verifier tells me, that now we can't prove termination. Well, that's because the indices did not move. Yes?
For the assignment key,
Yep.
I did not complain.
Yes. Thank you for asking such an advanced question. Daphne actually allows you to write, it says here, note that the loop has no body. It lets you write the loop without the body, actually, because if you write, suppose that you write a method and you want to write a portion of that method as a sub-method. That is, you want to call it as a subroutine. Well, what you can do then is you declare the signature of the other method, you write its spec. Now you have a choice. You can either continue writing the program where you were for the caller, or you can go to the callee and write its code first. And you have a choice. So it seems like, well, why shouldn't you have that choice when you write the loop? Here I can then write the spec of the loop, and if I want to, I can, if there was more stuff to do after the loop, I could do that here, something like that. And then go and write the loop body later. That's just what it allows you to do. And that still means that it's using the loop invariant to prove the rest. So you can see that you got the loop invariant correct by that time. Okay, thank you for that question. Okay, let's do another little demo. Here is so the previous program then used arrays and loops, I mean a simple one, but here I'm going to do a very simple thing in a functional style. So I have an inductive data type, and I have two functions, length and append. So what do you want to do with something like this in a functional setting? Well, you want to prove something about it, that append and length are correct in some sort of way. You can do that using a lemma. Let me scoot this up a little bit. So what I'm going to write is I'll call it append length. So the append length lemma it's just a method really. So it takes two arguments, two lists, x, y, x's and y's, and I will give a post condition to the lemma. What does that mean? A post condition of a lemma is the conclusion of the lemma, just like you write a post condition of a method. So if you know how to write a method, you can write the lemma. And here I'm going to say that the length of append of these two is the length of the one plus the length of the other. Okay, that's what I want to prove as my lemma. So how could I possibly write the proof now? Well, remember, a lemma is like a method, so I'm going to write some code. So what I do is I start the body here, and what's typical in a situation like this is that we do a case split on some things. We use a match statement, so we have two cases to consider, like that. Okay, those are the two cases, and now we get an error message here. It says that the post condition does not hold on the path of nil. Well, nil is supposed to be the base case, which is supposed to be simple. Going on. Yes. Ah, yes. Actually, this is an error in the append. So this should not return nil. So actually, this detected an error. By the way, when I wrote this morning, I actually made this mistake, and I was surprised. And of course, as the tool developer, you always go, why is my tool not behaving? And of course, the tool is usually behaving really well, and it's the program that you're trying to verify that's not good. Okay, and now you can see it's switched to the other case. So let me write that case. So now I'm going to use a feature that's not in a programming, that's not a feature that you would program with, but it's a feature that you would use when you prove things. And the Ironclad and Iron Fleet projects I mentioned, when they proved things about their programs, they would very often break into these proof calculations. So there's a statement in Daphne called calc, for calculation. And what I'm going to do is I'll start with the left-hand side of what we're trying to prove, which is this one. And we're trying to prove that this thing is equal to that right-hand side. So what I'm going to do is some transformations, and eventually we hope to end up at the right-hand side. Okay, what can we do now? Well, remember that that xs, well, what should I call this? What xs is. So in this case of the code, so this is just, the match statement is just a programming statement. So we know control flow, when it reaches here, xs is equal to this thing, right? So what I can do is just replace the xs here with cons of what I know that is, okay? And I wrote a little English comment here to remind myself of what I did in this proof calculation step. By the way, am I too far into this? Should I move? All right. So, okay, what can we do now? Well, now we can apply the definition of append, because we have an append of cons, as we see here. So append of cons was given up here, right? So what I will do now is I will replace append of cons with, I'll just copy that here, because luckily I used all of the same variable names, so that was good. Okay, and again, Daphne, the tool, checks that the step was correct. But we're not there yet, so what can we do now? Well, now we'd like to apply the definition of length. So when you take the length of a cons, you get 1 plus the length of the other thing. Okay? So far what I've done is I've just applied definitions, right? This is not rocket science. Oops. Okay? So, but now I need to do something. I need to somehow reason about the length of append of tail and ys. What would you do? I just didn't hear. Yes, apply the lemma recursively. Exactly. So I'm glad to hear that you're thinking as a programmer. So we're going to apply the lemma recursively. This is called the induction hypothesis in mathematics. So in the previous steps, I just gave little English hints, comments. Here I'm going to give some code. So I'm going to start a curly brace, a code block, and I'm going to call the lemma recursively, and I will call it on tail and ys. And that gives me, let me copy this, that gives me that, the length of append tail ys is the length of tail plus the length of ys. Okay, that's what the induction hypothesis tells us. And now we're essentially, Daphne is happy now, but if we wanted to fill out the rest, we would say, well, the 1 plus the length of tail, that's equal to the length of, well, let me just write it right away, of xs, right? You can be more explicit in these steps if you wanted to, right? So that is the proof calculation. So this is the kind of style that you would write proofs in Daphne. And these operators on the left-hand side, they need not be equalities, they can be whatever other operators. But of course, Daphne provides some automation. So what I've done here is, I just, for the demo, I turned off the automatic induction in Daphne. So so this calc statement, really, the most important thing is just the call here to the induction hypothesis. So in fact, Daphne can figure out the rest if I just have that call. And with the automatic induction that I now turned on, induction hypotheses are usually applied automatically. So that's the proof, which is a pretty simple proof. Okay. Questions? Okay. So let me just show you another program that I'm just going to show you real quick. Here's a majority vote algorithm. That's just another kind of array algorithm, if you will. That's kind of fun to verify, and it's a cool algorithm. Boyer and Moore did it. What I want to show in this algorithm is that it's an imperative program, so you have some loop invariants. But it turns out that to prove this program is a little bit trickier. So you need 2 lemmas. And so these lemmas, remember, a lemma is just like a method. So you call it just like a method. So you call it in the code. So when you compile this program, lemmas and other ghost things are just erased. But it's in the program. And we can see the lemmas down here. And since I've now turned on automatic induction, there was no reason to do those sorts of things. Those are simpler. You can, of course, keep the proofs if you want to. If they look nice. But so this is an example where we're mixing programs and lemmas. Okay, so that gives you a flavor of the sort of things that you can do with programs. So now what I'd like to do is go beyond programs. So I'm going to consider now something that programming language people like to do. And that is you define the semantics of a programming language, and then you prove some properties about it. Every other POPL paper does this in some form or another. And of course, if the program that you want to verify is a compiler, you're going to have a specification for the compiler. That specification is much more complicated than the little array programs that I wrote. So there you need something, for example, like the semantics of the source language, the semantics of the target language, and you prove that your compiler does a correct translation between the two. So for the purpose of this talk, let's just consider this really simple and rather useless language. It has 3 commands. It has an increment command that just increments the state. So the state is going to be an integer. And it has sequential composition, and it has a funny kind of loop. So this loop can do 2 things. It can either just, well, actually, what the loop does is it just some number of times repeats that command. 0 times, 27 times, in an infinite number of times, who knows? You have no control over it. A better programming language might give you a guard there, but not today. So I'm going to give the semantics of this language, just to show you what you typically do here. And I'm going to give it as a relation that takes a command, a pre-state, and a post-state. So this is the typical kind of big step semantics that you might define. And but this is what CST is saying is that there is some execution of the command C that if you start it in state S, it will terminate in state T. It does not say if, there could be many other executions and so forth, but this says that is a possibility in the language. Okay, so how do we define this? Well, if you're writing a POPL paper especially, or if you're convincing a colleague, whatever, you probably are going to write down inference rules like these. So we have one inference rules for inc, which says that inc goes from S to T if you know that T is 1 more than S. Okay? Sequential composition says that it takes you from S to T if you have an S prime such that C0 goes from S to S prime and C1 goes from S prime to T. No surprise, you probably have all read many rules like this. And the repeat has two different rules associated with it. Either it stops, so repeat can go from S to T if T and S are equal. That's one possibility. And repeat can also go to S and T if you can go from, if the body takes you from S to some S prime, and the S prime is a state that repeat takes you to T. Okay? So that's just the definition. So before we do this on the computer, I just want to remind you of something that you already know, and that is that when we write S prime above the line, what we really mean is that, because there's no occurrence below it, we really mean that there exists an S prime such that the thing above the line holds. Okay, so just remind you of that. So let's see. So what I'm going to do now is type that in. So here we have the data type command, and I just made a type synonym state just to make it look nice. And I will define a predicate. I'll call it big step. It takes a command, it takes a pre-state and a post-state. And now I will define it. I will define the predicate again on, I will consider three different cases depending on what the command that we're given is. So we might be in the inc case, in the sequential composition case, or in the repeat case. Just like on the other slides. So if the command that we're given, C, is the inc command, then when does this predicate hold? Well, it holds if T is one more than S. Okay, so I just write that down like that. What about for the sequential composition? Let me flip back to the slide to remind you all. Well, it's this one. The sequential composition takes you from S to T if there exists the middle state S prime. So let me write that. There exists a middle state S prime such that big step holds of C0 from S to S prime, and big step holds from C1 from S prime to T. Okay? And what about the repeat case? Well, repeat, there are two cases. So there are two situations under which you get the repeat. Okay, so one case is that S is equal to T, and the other one, so it's either S is T or there exists an S prime such that, again, big step body takes us from S to S prime, and big step goes, well, here I can either say repeat body, but I have a name for it, so it doesn't matter which one I say, but the whole command C, again, you repeat the loop again from S prime to T. Okay? Does that look all right? That's kind of the definition that I had. But Daphne is not very happy about this. And Daphne complains that it cannot prove termination, and it gives a little bit of an excuse. It says, try supplying a decreases clause. I mean, so it's admitting the possibility that maybe it just couldn't figure it out, and the program really does terminate, so if we just help it along a little bit more, it would do it. But in fact, in this case, there's no reason at all to think that this recursion will terminate. C and T are exactly as they were before, and that's S state, who knows? I mean, what that could be. There's no reason to think that this would ever terminate. In fact, the loop is allowed to recurse forever. So, here we need something different. And the something different that we need is a realization of what do these inference rules really mean. So when we define the big step by these inference rules, we're essentially defining that big step is some function in terms of big step itself. That is, where f is some sort of functional, and big step in this case is the lambda and so forth. And when you write so what you'd like to do is when you have a fixed point like that, there are different solutions for big step. So big step may have several different solutions. So we need to decide which fixed point we want. And it is typical in mathematics that we want either the least fixed point or the greatest fixed point. And somehow we're just never interested in anything in between, but that's okay. So there we are. Now we're doing this on the web instead. So what we need to say that this is the least fixed point. And the way that you do that is you declare the predicate to be an inductive predicate. Inductive predicate just simply means that what we give it is going to be the least fixed point. And then it allows us to write this. It just checks that the function is monotonic. And I could have said more about that, but I won't. And now you can prove from this that the semantics, if you're given that someone has proved the big step of CST, you can prove that means that the state T is at least that of S. In other words, the counter, the state never goes down. And you can prove this using yeah, there it is. It finished. And in fact, actually, it turns out that this too, you can. Daphne does a lot of automation, so I expect I will be able to do it with. Well, with a lot of automation. Yes, there it is. Okay, it verifies. Okay. Daphne behaved, but my computer did not for the demo. Okay, so here we are. Can I use this? Copy it here, or did I just? Up and down. Oh, well, I don't know. Okay, so we want the least solution. Okay, let's see if it. Since I pulled the plug on it here, we'll see what happens. Okay, so let me go on to say, so what I've shown you so far is that you can verify programs, you can write lemmas, you can do induction, you can even do inductive predicates that are predicates defined by least fixed points. And that's rather advanced for something that's sitting just on top of a first order SMT solver. So let me end by saying some things about where we could go from here. So we have the source language. The way that the verifier, like Daphne, is built up is that you translate it into an intermediate verification language. Peter showed Viper yesterday, and Daphne is using Boogie. That's another one. So what you have, the advantages with having an intermediate verification language is that you have a separation of concerns, just like you have in software engineering when you write a compiler. The front end of a compiler has different concerns than the back end. So, and what's very important with the intermediate verification language is that it's something that you can look at and read and edit, because what you do as the tool developer is you write down, you have some verification that doesn't go through, and you want to debug it somehow to figure out what should your verifier do better. And this is not what the user does, but the developer of the tool does this all the time, and then you want to be able to edit it. In fact, Ari's also had, I think, 2 intermediate hops in his verifier. Okay, so this is something that you'd want to do. And I might have shown you this, but you could imagine how this goes. So now where can we go from here? Well, something that is a good feature with this pipeline is that it's fast. Something that you might want to do more with is that it's not certified. That is, what you get afterwards is something that is only as good as what the verifier is and what the intermediate language is and what the SMT solver is. So that's a large trusted computing base. But the human time is spent in the editor interacting with the prover, and that time is fast. That's what you want. You don't want to waste the human's time. So there's an opportunity here, which is that one of the authors of the Z3 tool, Leo de Mora, has the last 3 years been spending time on a new prover called Lean, which is, well, to say it in a word, it's cock-like in that sense. And but knowing Leo, I mean, he puts in lots of automation, he builds it, and it's a new tool now, right? So the cock has decades of legacy, so maybe there are some decisions that one can design slightly differently. So if you look at that picture, of course, there's an opportunity here to put something in between. And what would it be called unless it would be called fat, right? So that's the first thing when you do research. I mean, first you have the name, and so let's think about this name a little bit. So we can have a little logo. So Ari likes designing logos also before doing research projects. So maybe fat will look like a pea hat, I don't know. Or maybe it would look something like that, fat, I don't know. That's for designing later. But the question is, well, what does fat even mean? Well, you go to Urban Dictionary, of course, and there you find out that fat means cool. So that's nice. I mean, I should sit on top of lean. Well, if you read the next definition on Urban Dictionary, it says, the problem with fat is that it's no longer in, really. It has been phased out and is mostly used by wannabes, lower classmen in high school or middle schoolers. It's now considered a slang faux pas. I wouldn't use it if I was you. So, but we shouldn't let that bother us, right? So, okay, so now what fat could do for us is, instead of going just down here, what we'd like to retain is the benefit of the speed that we get from something like Boogie and Z3. So we'd like to have two paths from fat, one that goes the fast way and one that goes the secure certified way. Okay, so let me give you a flavor of what this might look like, and it will be a little bit quicker. So I'm going to show you two idioms that you do when you translate into Boogie. And these idioms are then things that we'd like to lift to fat, if you will. So if you have some source language proof obligation, here I'm showing it as a condition Y, as an assertion, in fact. You, of course, can do that in the intermediate language by checking that the condition Y holds. But very often what you do instead is you check X and you assume Y. Well, that's not sound in general. I mean, you can't check something else. So I'll call this idiom the check what I say, not what I assume idiom. And, but of course, when you're the tool developer, you have some reason to think that it's okay to check just X when you want to prove Y. So here's one example. Maybe you want to divide up the proof obligations from the program text to divide them into conjuncts so that you can give better error messages about which one failed. Then maybe you have two assertions and then you assume Y. In this case, it's probably pretty easy because Y is probably the conjunction of those two, maybe. Here's another example. Suppose that you wanted to prove something, a universal quantifier in the program text. Well, maybe this would be made simpler if we had the induction hypothesis. So what you do is you throw in the induction hypothesis as part of the thing that's being checked. And then you assume the real thing, because of course you don't want to assume the thing with the induction hypothesis. That defeats the purpose of using induction. And we think that these two are the same, and they're the same because of because of the induction principle that you prove somewhere else once and for all. Okay. Here's the other idiom. The other idiom is that when you're in a situation like this, you're going to check X, you're going to assume Y. What you very often do is you want to check X, but that may produce a large proof in the for the SMT solver. So you want to forget that afterwards. And you can do that by this construction, which I will not try to explain here. But for those of you who know the assume command, you will recognize the assume false as you can read assume false as, listen to me, forget about it, right? It's so you check X and then you get there and forget about that path and just go to the other one and assume Y. Okay, so that's the kind of thing that you want to do. And if you have two of these, it might look like this. Okay, so those are two idioms. So going back to fat, we'd like quick turnaround verification of the source program. So we'd like to be able to take those sorts of things and just feed them to Z3 and get good, fast checking. But we also want the soundness of it. So here you could do a lot of things that interactive theorem provers do with like deep embeddings of various things. And let me just show one path that suggests how one might maybe do this. So here is that proof, the intermediate language snippet again in the middle. And what I've added in italics are, whenever that assert is proved, I'm capturing that what it proved. I'm getting the proof in my hand, and I'm calling it A. So if you're used to something like cock, you would have something like prop, and you would have all sorts of complicated things. And this is going into that complicated territory. So I'm capturing the proof, and then also I'm doing the same thing for the X1. Well, given that, when I then get to the assume, I can say that it's okay I need to justify every assume statement, and I can do that because I believe that A and B imply Y. Now, it's much more complicated than this in general. It's not just conjunctions. It's maybe here you need a lot of meta reasoning. You need additional invariants about your encoding. And for this particular slide, you may have noticed also that A and B are actually assigned in the then branch, but I'm using them in the else branch. That certainly does not look good. And there's an assume here as well, assume false. How can I possibly justify assume false? Well, that's also to think about in this setting. I'd be happy to discuss those sorts of things at coffee. Okay, so the point of having this dual encoding is that you can erase all of the italic stuff and go the fast path, or you can, because that's on the user's clock, that's when it has to be fast. And you would expect that the verifier is probably correct in many cases, and so therefore that's a fine thing to do. That's on the user's clock. And then overnight you can run the certified thing, and it probably won't take that long either, but if it does, it's okay. Okay, so let me conclude. So I've argued that program verification today is accessible not just to formal method specialists, but it's also accessible to people who really want to do verification. That is, who are willing to take some arrows in their back, who are willing to learn what specifications mean, who are willing to do the proofs. But it still is palatable for such a person, and that's good. Something that's also very important is to be able to teach students about formal methods, about preconditions. Every student should know what the precondition and invariant is. And having a tool around is a really great way to do that, because with a tool you can have many round trips to the tool in just a little sitting, and then we figure out these things. In analogy, we don't learn about grammars and things like that to explain why there's a missing semicolon in our program. If you're sitting at the program editor and it tells you there's a missing semicolon, you just fill it in. You don't know what technology is behind there. And so but we learn that that's how you do it. So if you learn that that's how you write a method, you write down the precondition and that's what it means, or an invariant, we would be in a better shape. And of course, many schools are teaching these sorts of things. And then finally, the point is that the high automation that you can get from a checker like these is not just for programs. I mean, you can do for student programs, arrays, simple arithmetic, inductive data types, induction. I mean, that works so well. But we can push the envelope there to do harder things, and it seems that you can write proofs and things for them as well. So here are 2 URLs. You can go and try things out yourself. Thank you very much.
Any questions? Yeah. Well, yeah, better go ahead.
Okay. I'm looking with very high interest what you have with the Lean your program. I thought in some way that Lean would somehow be able to describe everything that you can describe now in Daphne. So what is the gap between Daphne?
Yes, it's an interesting thing. So Lean, I mean, overgeneralizing, but one way to think about Lean is that Lean is a Coq alternative, right? So Leo is trying to provide more automation for various things, and it has this tower of universes in the logic and all sorts of things, right, that you can do. So if you want to prove something about homomorphisms or about the four-color theorem, I mean, that's the kind of thing that you would use, and it would produce certified things. But Daphne is also a competitor to Coq. If you want to do semantics like I showed here, if you want to group programs, Daphne is generally much easier to get started with. So in that sense, I mean, the two are similar. What you cannot do in Daphne is you cannot go to various universes of logics and all sorts of things like that. That's just not, I mean, it's not there. It's, you're in this smaller logical universe. And that universe is usually good for most of us. But so there's larger effort in using something like Lean, but you get the certification. Daphne is easier to use, but at the moment it does not give you the certification. But it could with using something like Lean as a backend.
So do you think the speed of Daphne, or?
I don't think that Lean will reach the speed of Daphne, because I mean Daphne gets its speed from the other path, right? I don't think it's going to get that. Furthermore, you don't really write a program in Lean. I mean, you write mathematics and you can encode programs and so forth. So I mean, if what you're doing is writing a program, you should use a programming language. And in Daphne, you compile, right? Which means you erase the other stuff and you just compile the code that you wrote. In a tool like Coq or Isabelle or Lean, you extract the code, which essentially means you pull it out of the proofs and so forth. So it's a different way of thinking about things.
Vitotas? Get it? No, actually, okay.
So when one verifies programs, at some point you understand the concept of the algorithm and you come up with the specification. But sometimes when you try to actually verify things, the bugs might appear in both worlds, in the world of the specification and in the world of the implementation. And so the question is, if something doesn't verify in Daphne, what are the best ideas or tools for supporting the programmer at that point?
So you want to debug your verification essentially.
Yes,
right?
and in situations which are very simple, you get some feedback, like Daphne might suggest that you need a decrease clause or something like that.
Right.
But in more complex situations, is there a way to facilitate?
Yeah, so Daphne does two things. One thing is that all of the red dots that you saw, you can click on those. That brings up the verification debugger. So then you get the context. And we would all think that, ooh, that's going to be really nice. And it's nice for some simple cases. But in fact, really what most people do is you're trying to prove something and you're wondering, I mean, why doesn't it prove this? So you add an assertion before it to say, I mean, do you know this? And then the verifier then responds with maybe, yes, you can prove that, but it still doesn't prove the other thing. Or maybe it says, I cannot prove that assertion, but now downstream of it, I can prove everything. So that's the kind of thing that you would tend to do to debug things. And this works because the system is fast. I mean, if you had to, with each little thing that you would ask the verifier, if that would take 10 seconds, if it would take a minute, 10 minutes, I mean, you would get so bored, and I mean, you would completely, I mean, look at your Facebook page would look lovely, but but you wouldn't, I mean, ever get back to it. You need that to be fast, and it is fast in Daphne, usually.
But what if the problem is that Daphne is incomplete?
Yeah, I mean, it is incomplete, right? I mean, we're above the decidability ceiling. You have quantifiers galore. You may have, I mean, it's certainly incomplete. So well, what you hope is that you'll be able to guide it with the lemmas that that are needed to prove the correctness of it. I don't know of any formal theorem that states anything about that, but it tends to work pretty well in practice, unless you get into nonlinear arithmetic.
Okay, so let's take the rest of the discussion offline because it's already pretty late. So let's take a coffee break now. I would like to ask all the speakers to meet outside because we would like to take a picture, and then we'll continue in around 20 minutes. So thank you, Rustan.